be okay for me to take like 1 or 2 more days to work on homework 4? Yeah.
Of course.
Okay, thank you.
That's fine. Well, it's the second, third course that you take with me.
Yeah.
Did I ever say something different?
Sure that you're still good with that, but yeah, thank you for being very lenient.
It's not like I ever submitted anything on time.
Oh, and did you release the grade for homework 3 yet? I saw you said that you already graded, but I didn't see it on D2L.
Send me an email to remind me and to find it. I finally started to make order with the names, and I just check what is the repositories that were recently updated, but it's
Yeah, usually D2L
keep sending me emails, that's the best.
Okay.
Put it on auto. Everybody's good with texture, with shaders. That is how you are computing approximated the UV coordinates and then looking at one of the texture images and doing the UV pixel. Okay, because let's talk about homework 5. So homework 5, don't finalize the details, but let's take about some of the components that you have. In homework 5, there will be a pool. And on the bottom of the pool, there will be an image. My best way of representing an image, a picture that is on the bottom of the pool. And you have the viewer somewhere here, and the viewer watch to the bottom of the pool, and at t equals 0, the water will be completely, let's ignore it first, right? To start with, so you have the bottom of the pool, and you just do, from the viewer, just look at texture, and you are done by this. Just one pass of Z buffer with one triangle plus the sides of the pool. But then I start to create restlessness of the water, wave ripples on the water, which means that the viewer now, if that's one of the ray, you're not doing ray tracing, just to make sure, but had you been using ray tracing, then this way, water, normally you would continue this way, and returning the color of the picture at the bottom of the pool will this way continues. Well, now you don't, because you are applying Snell law that will imply that this way, depending on what is a curvature right here, what is a tangent of the water at this particular time, the ripples moves with time. It could be a simple sinus that changes with time, which means that now the color that you apply, how you do ray tracing once again, the color of this pixel P is not the color of the ray at P, it's the color of the texture at P prime, where you continue it to be, you continue it straight. Okay, so you can assume that the amplitude of the wave is quite shallow, which might not make sense physically, but it will still mean that the intersection point, this point is just the point that you are getting from the ray, or just the point that you are getting by normal interpolation, just the coordinates of the top of the plane interpolated with barycentric coordinate. This is just a fancy way of saying, take this location from the vertex shaders into this fragment, and this fragment by itself, its position is as if the water is flat all the time. Again, it's positioned as if the water is flat all the time. That's where I care that the amplitude is low, that the waves are not too high. Otherwise, I would have to do some more math to compute the intersection point. But once I found the intersection point, here I need to, at this moment, I do need to care, and I'll give you this formula of what is a tangent of the water right here, which gives you an angle that you shoot, which gives you some displacement. And instead of looking at the texture direction uv, you're looking at position uv as if it was straight. Snell law will means you're looking at u prime v prime, and u prime v prime is kind of easy to calculate, and we'll go through it in more detail. So that would be one effect that you add to the water. And guessing what's the other effect that you add to the water? But one effect that was in previous homeworks was to have the sun creating the patterns on the bottom of the pool, and to make it realistic is a bit hard. You can do it with some hex, but because if you think of one point in the bottom of the pool, I need to integrate lights that coming from different directions to the bottom of the pool. Makes sense? Just like if I take my lens in the focal and many points. So let's not worry about this part, about the pattern of the sun. So it's cloudy day, but guessing what else the color should reply?
There could be some specular effect.
Pretty much. Here is a tree, or something in the background, which now implies that there is also a refraction at the bottom of the pool that you are using similar. Ideally, it's even simpler than Snell law. Everybody remember what is Snell law from the many students in this classroom? Okay, and that's will be just fancier usage of shaders. Not too hard with ray tracing, but very slow. Want to have it in real time, use shaders. Okay. So I have a segment that connects A to B. I'm sure you just want to re-explain. I have actually a few examples, probably over-explaining. I have the point A and B, AX, AY, BX, BY, and for a time t between 1 and 0, here is the point P of t, whose coordinates are t t b x plus 1 minus t b y. That's 1 minus t entirely. And I lost my plus 1 minus t ax. That will be the x coordinate, and of course the y coordinate will be t by plus 1 minus t ay. That's how I represent every point along this segment. I just did it in a more obnoxious way than normally. So that is point over here. And when I change, I don't call it t here, I called it u, but when I move u from 0 to 1, this point moves along the segment. And now I want to make it into a surface of revolution. I want to take this point on the segment. I want to take this point of the segment, and that will be a radius. So I'll treat for this particular time t as the radius of a circle. Radius of a circle that you can see over here. When I move the point, of course, this circle changes its radius. Now, where is the center of the circle? At time t or time u? What's the coordinate of q? It's written. Yes? Coordinate of q will be 0, x equals 0, and y equal y of p of t, which is just this second parameter. That would be the radius at this point. That's this point. What will be the radius? The radius changes as I'm changing the time. Oh, but the circle touches the segment all the time. So here is a circle. Just when I flatten it, notice the y is vertical. So the radius is nothing but the x coordinate of a of t. Whatever it, just as I said, the coordinate. So when I create a surface, one parameter is t, that goes from 0 to 1. And another parameter that I'll use over here is when we'll be taking this point. This formula will appear multiple times. Well, I'll take this point, and let's think about r cosine v and sinus v. So I need two parameters, u and v. I'm creating a surface, it has two dimensions. Curve will have one parameter, one dimension. Surface is with two parameters. So it will be, when I'm changing v over here, what happened to my point? The radius stays the same. You see the same circle here. I'm looking at it from the top. That is, I'm standing right here at infinity and looking at the circle. And the radius, what did we say the radius is? The x coordinate of the segment. And now by changing v, I'm just rotating it around it. Changing v, once again, changing v. making these segments turn around and round. Changing U, I just specify where this circle is. And here it will be when U is between 0 and 1 because it's just one segment. We'll see more interesting examples coming up. So here I'll use the radius as the same coordinates. Here we are rotating it around Z. More examples coming up, so don't hang up on this slide. The Z coordinates is just what used to be the Y. I'm just rotating around the Z. So that the curve, now it's curve that is parameter again by T. The height, the circle, depending by the the Y coordinate, the Z coordinate. And here I'm using B of X, just as before, as the radius, times cosine and times sine, creating a circle around it. Altogether, creating a surface of revolution. Which give us the first excuse to have splines. I want to create surface of revolution. Now it will be complicated, so I'll have to tell you how to generate a spline. I have a set of input points. The designer is inserting a set of input points, A, B, C, D, E. The spline, B spline in this case, is a curve that in this case goes through all these points. It might have some hiccups when it starts and when it ends. T will change, so watch the point P of T moving along the curve. P of T over here, start from one side of the curve, one endpoint of the curve, and changing to the other endpoint. We talked about it. Why do I want it to be an implicit curve, P of T, and not just y equal f of x? Because every such function for every x just fit one line, one value of y. I could not have this curve going crazy, which I could do with B-spline, or with spline in general. Still the same curve of revolution, still changing T now. Looking at this curve, it's for every point P of T, look at the x value of P of T, that's a radius, the same radius that you see over here, and taking this radius multiplied by cosine V and sinus V, the elevation of this point, the center of the circle, is the elevation right here, which is the y coordinates of P of T. P of T, 1 point that I fix the time. Look at the circle that it's defined. The radius will be the x coordinate. The elevation would be the y coordinate, and once I change it, it's defined a circle. And what I also show in this app is now I can move just U. Does it work? Does it not work? When I'll start to consider all the U's between 0 and 2 pi, rotate this curve around the y-axis. So eventually create the whole surface of revolution. Once again, here is if I just move the points for one particular time, and here is if I'll just let it rotate altogether. Any questions? Everybody understand how do I get to the formula from it? I still didn't tell you how I create the spline itself. But once I create the spline, that is A, it's vector A of t, which always in R2 in the xy plane, taking A of t, and I want to rotate it around the y-axis, I will look at x of A of t cosine v. I need to decide about the elevation. Y, it's A of t, y of A of t without anything, because it's a y coordinate. That's how high I am along the y-axis. Just think about the center of the circle. And what will be the z coordinate? X A T sinus V. How do I know that it's always in the same circle? Because sinus square plus cosine square is always 1. Okay, so that's about surface of revolution. Now let's talk about splines. And I'll first introduce B splines and then talk about more basic splines and then move back to telling you about more splines. So, you know, the whole deal about curves, huge area, many results. Extremely useful. You have a shape in your mind, and you want to tell your computer that's a shape that I want. And I would like to have a few parameters. I don't want to draw, even in 2D, I don't want to draw infinitely many points to denote the curve. Even if I'm just in the business of surface of revolution, we didn't talk about other shapes yet. Surface of revolution, something that is centrally symmetric around one line. I can draw infinitely many points. Or I can draw a set of control points, P1, P2, P3, P4, and ask the computer do linear interpolation, that is connect P1 to P2 via a straight line segment, P2 to P3, P3 to P4. And I can make surface of revolution, nothing wrong with this. In this case, what should I do in terms of time? I will say in this case, when t is between 0 and 1, P of t belongs to the first segment, S1, the one that connects P1 to P2. When t is between 1 and 2, then P of t belongs to S2, next segment, and so on. And when t will be between 2 and 3, it will be on the third segment. And that's a good start. That's what we are going to do later, and that's already a spline. Ugly spline, but a spline. I concatenated the segments, and I made the time continuous. And notice, by the way, that it's at least continuous, because when I'm on the first segment using the same formula of interpolation, when t equal 1 and I'm at the end of the segment, then it will just be when t equals 0, but consider the second segment. So, of course, you're not using exactly this formula, but this formula will work only for the second segment, for the first segment, and then if you want to continue it to the second segment, we'll say for t between 1 and 2, I will do similar trick with the weights, except that I'll move the weights by -1, and the control points would be B and C. Make sense? I think that the more I'll describe it, the less obvious it will be. Yeah.
So do the points have to be either one distance away, or can they be a longer distance?
It will be longer distance.
Okay.
And we'll We'll not discuss it today, but actually in B-splines, we'll see how we can make points more important, less important. What's wrong with this? It's continuous. Great. Its local changes only influence local parameters, the local behavior. I move one of these control points, it moves only 2 segments. I can go also to the opposite direction and say, hey, you have 4 points. 4 points is too few. 5, 6, 7. I have 7 points. Let's fit a polynomial of degree 7. Polynomial of degree 7, the constant, the highest exponent is 7. And you can always do it when you have 7 points. When you have 8 points, there is a polynomial of degree 7 that fits, go through them exactly. That's nice, except that it's not recommended for various reasons. To start with, local changes will spread to the whole curve. If I'll move P1, say if I'll take P4 and I'll write P4 right here, very close to the original P4, everything along this curve will change. If that's what you want, it's fine, but probably not. Can you easily find root of polynomials of degree 2? Yes. X12 equal minus b plus minus, etc. Can you easily find degrees of polynomial of degree 3?
For
Sorry?
For some special cubic.
Practically. I'll give you a polynomial of degree 3, and the roots are all real. Yes. There is a formula, I think, that even in general, but it took hundreds of years, and that's not what I'm after. Can I still do it? Easy. Using nothing besides the knowledge that you had when you finished high school.
Because you could factor it and then solve for a 0.
But how can I factor? Just to make sure, I can always write if I have a polynomial ax cubed plus bx squared plus cx plus d, that's p of x. And I want to ask where is p of, and I want to express p of x equal x minus alpha times x minus beta times x minus gamma, alpha, beta, gamma. A, B, C, D are always. And you can factor it and actually, but how? You all know the answer.
Can we take the first set of the expression, it's like the x cubed plus x squared plus x, and then factor on x and then solve the quadratic there? So like you easily take the x out, solve the inner one.
I have mixed feelings about it because I think that actually it might be related to method that is valid, but I don't know how to use it. So I'll call it no. Maybe, but I don't know that it's actually a factor. Like, maybe you're right, but you all know the answer.
Do we draw the graph to estimate the intersections?
I want to know pretty much what are the roots. And once I found one root, then the other two I can just factor, and then it's quadratic, and then the other two it's easy. Yeah, just quadratic equation. But the first root.
Is it for the general case or?
For the general case.
Then I think there's an easy.
Can somebody draw the graph of such polynomial? What's the general shape of such polynomial? Let's say that A is, let's start, assume that A is 1. You can always assume that A is 1, yeah.
And assume alpha.
A is 1, that's the only thing that you know. Show me the shape of this polynomial in general. He's right, but why? What happens when x is very, very negative? X is minus infinity. A is 1. X cubed must be minus infinity. Right? Going very to the left. X very tiny must be negative. Let's take x really large. Because A is positive, well, must be positive as well. Why? Because the other terms, no matter what they are, if I take x large enough, the other terms measure less than the x cube, and x cube is the same sign as x. Okay, so I found 2 points. One is positive, one is negative. Next, do binary search. Just, finding a lion in the desert. Just do binary search. If that's negative and that's positive, if I take the middle of the row, just binary search, then it must have different signs, and either this or this, meaning that because of continuity, there is 1 point. That it's a Google question, I think.
Oh, so it's more like an estimation and not like the actual.
It's calculation, it's approximation. Do
Okay.
binary search after log n many steps, you are as close as you can, but you're right that it's not a close form. Anyhow, so polynomial of degree 3 practically we can handle. Polynomial of degree 4, etc., all hell. So we want only polynomial of degree 3, but then I have plenty of control points that will naturally leads me to the idea of B of splines. Let's somehow stitch them and make the stitches friendly. Another question for you. P1, P2, P3, yada, all the way to Pn. And look at the shape sigma Wi. It's not the first time we handle this question. Sigma Wi, Pi, Wi's are weights. All positive. And the sum of these weights is 1, what we call convex combination. What's the shape that I'm getting when I consider all possible weights? For this set of points, remember? If it's 2 points, what did I create? I create the segments between them. If there are 3 points, I created the triangle. If there are 4 points, but not in convex position, I just created the triangle once, again. If it's 4 points in convex position, can guess yourself what is convex position. I create the whole polygon itself, and normally I create the convex hull. Convex hull of the set P1 all the way to Pn. Remember what's convex hull? You can think about it as the smallest polygon that encapsulate all the points with the minimum area, or think about it as place a rubber band and let this rubber band snag, or nails that you are putting, and so on. So that would be something to keep in mind. Easy to calculate. Well, we like splines, we like polynomial of degree 3. It would be nice if it would be a symmetric invariant, rotation invariant. If I rotate my control points, the curve should normally rotate. It should not be preferable to particular x direction or y direction. We'll talk about more continuities that are also desirable for different reasons. Let's talk about B splines. So B splines, we are creating a curve, C of t. Creating a curve C of t, how? For every t in the range, I will look at all the control points, pi, all the control points, and for every point I'll give some weight. And the sum of these weights will always be 1. And for every time t, every point t, I will specify 1 point on the curve. That was very general, not very clear. And here you see what is a generic weight function. Generic function is something w of t. Nobody understands anything at this point, but bear with me. W of t depends on t. It's a weight function changing in time. When t is very small, smaller than -2, it's 0. When t is very large, larger than 2, it's also 0. So that's your weight function. A bit similar to Gaussian, but it's not. T is more than 2, it's 0. T is -2, also 0. And then it's symmetric around the 0. It go up according to how to see, but that's t plus 2 to the power 3 divided by something. There is explanation of why this polynomial. That's between -2 and 1. It's one particular polynomial. It's exactly the same polynomial, just in the reverse, from 2 when you're going backward to 1, and a different polynomial from -1 to 0, which is symmetric from 0 to 1. Why do I need all this gymnastic? So in general, what we said, I'll give every point pi some weight wi, and what is this weight? Wi of t is roughly t minus I. Desperately need explanation. Wi of t is this function w of t, except that where is the I? It shifts the time by 1 unit backward, 2 units backward, 3 units backward. Let's see what's happening. So first, here are my polynomials. Wt in general, here you see it. As we said, t is smaller than 2 or t is larger than, t is smaller than -2 or larger than 2, it's 0. And here are the different weight functions. This will be the weight function, the purple one will be the weight function that, let's go to, on the left side of the screen, you see a set of control points that I specified. A, B, C, D, E, F, G, that are my control points. And I want a curve that will try to follow these points. Maybe I will miss a point. I don't insist on going exactly through the points directly, but I definitely want these control points to influence the curve. If I'll pull F, the curve should be pulled. Accordingly, if I'll push curve, the curve should react. But at the same time, I want somehow local changes only. And at the same time, I want this curve to be very, very smooth. So again, smooth, simple to compute, local changes, and so on. And B-splines will get all of it. So here is a W of C. What is W of C? Is W, but D, C for whatever reason, it's not a third, it's a fifth. I'll explain later why this strange gap, why it's a fifth, is W, except that the time don't start immediately, not at T, but at T minus 5. That is what the point C thinks when T elapsed. Only when T equal 5, the point C thinks, oh, T just start walking, T is equal 0. When T equals 6, then T minus 5 is 1, and what C thinks, the point C thinks, is that T equal 1. What about D, the next point? It's W of T minus, typo, T minus 6. Apologies, I will not correct it. That's T minus 6, so the time happens 1 year later. What about E? C, D, E. T minus 7, then it would be T minus 8, T minus 9, and so on. Look at these small numbers next to each one of the points. So I start to move T, and what the weight that D gets at this moment. The weight that D gets at this moment with WD is W of T minus 5, which is, since T is only 3, D thinks I'm getting 0 weight. So we had that C, the curve, we should use a different letter for the curve. Let's call the curve gamma of T. C is taken here, so gamma of T, the curve, for every fixed T, this is a single point, and this point is sigma of all the control points, Pi, that's my control points, times W of T minus I. It's actually T minus I plus 2, but we'll discuss later why this is not a T minus I. That is, it happens a bit later. So A thinks that when T equals 0, A gets all the weight. T was 0, A gets all the weight. Why this is not 1, we'll explain later. And B, C, D, E, F, each one gets 0 weight. I start to increase the time, and let's ask what's happening, say, right now. The weight of B is 0.11, the weight of C is 0.65, D 0.25, E still 0. What about FGH? 0. What's the sum of these 4 weights? Sum of these 4 weights is 1, always. there is only at most four, maybe three, four of these functions that are not zero for any particular time. Why is this cool? It's cool because where is the point on the curve, Q of t? Where is Q of t? It is in the convex hull of the four control points that are relevant to it. As the time elapses, here are the weights on this curve that are moving. I'll increase the weights, I'll increase the time. The points on the curve are the individual weights. The weights changes, but only four weights are non-zero at each moment, implying that where is the curve at this moment? It's a convex hull of, in this case, B, C, D, E. T will increase, then the last point in the sliding window will get zero weight, and on the other hand, F will start to get weight that is more than zero. Okay, so each moment there is a sliding window of the convex hull of these 4 points, and that's exactly where I'm proving the local changes influence the curve only locally. But if I'm changing the location of F, there is only one connected portion of this curve that F is in the game. It's not in the beginning and it's not in the end. Okay? Not far away, just this part where W of F is similar. And now you understand what are all these functions. It's the same weight function, just translated by one each time. If I translate it by different parts, it's, if you want to Google for it, it's called knots, okay? It can give me more important or less important to some points that I want to be more dominant or less dominant. Okay, and that's B-splines. What is this anomaly with why didn't I say that the W of 8 is 0? Well, if I do it in the elegant way, my curve will not start at A. It will start at some convex combination of A, B, C, D. Not necessarily in A. What the heck that allows me to make the curve, to force the curve to start at A, repeat A a few times, like 3 times. Not elegant, but good enough. But that's why the weight of C is not a third point. It's because A appeared twice or 3 times. C is a 5th point. A appeared multiple times, and the same goes if I insist that the last point, that the curve will go all the way to the last point. Now, just to make sure that in the same page, when I'm saying W pi times W of I mean that that's Q of gamma of X or Q of X, this point. What does it mean? That for when I fixed the time, I look at the X coordinates, takes the convex combination, the average weight of the X coordinates, takes the average weight of the Y, takes the average weight of the Z. Same weights, but of course the value of the X, Y, Z are different. And that's how you create B-splines. One of the types of splines that people are using. What other things can we say about it? Well, is this continuous? Needs a proof, but yes, it is. There are no gaps, doesn't step in between. What happens when I look at the tangent of this point? To create a direction of it, I need to take this weight function, and that starts to hint why are all these strange constants out there. Well, first I want, this constant comes because I want that the sum of the weights to be 1 for every t. And furthermore, if I'll take the derivative, well, how does the derivative change? The derivative will also change continuously. polynomials, when you take derivative of x squared, you know is x, change continuously. Derivative of x cubed is 3x squared, change continuously, and so on. We'll meditate more about these points, but B-splines will be continuous. What's to say against about B-splines is that it's very hard to force a curve to go through one particular point. Unless I repeat it, well, I can put D and I can put E at the very same, and I can put D and E at the very same point, but now the smoothness is not guaranteed. If I have 2 points that are just standing at the same point, smoothness is not guaranteed. Why do I care about smoothness? Well, you want to map, for example, a shape, a pattern into it, using it for surface of evolution, and want to have a nice matching to it, or want to create nice reflection, or want to create something that actually fly or move in the water, or something smooth, and that's where you don't want to create this. Of course, not discontinuities, not holes, but also want that the slope will change continuous as well. That's why we need other polynomials, other tricks as well. But more or less, we are done with this type of splines. And the name is as meaningless as I can think about why B-splines are. These splines in particular, I have no clue. Because we will see other splines, but they don't call B-splines. Hermit curve. So I create a different Lego piece that I can make into splines, into Hermit splines. Here is one curve of the Hermit spline. To create this segment, not a straight line segment, to create this segment of the curve, I need, if I'm using Hermit coordinates, I need to have 4 inputs. I need to have first, what is A, where this curve starts and where this curve ends. That's part of the input that I must give. And that's already a good start, if I want to have another curve to make it into a spline stitch pieces, then the next spline will just start at B and end at C. And just the time will move from 0 to 1. Okay, so to start with, I need to give it the starting point and the end point. But for this issue, a straight line segment will do just fine. What was my issue with straight line segments? That it's anything but smooth. So the other parameters that I want to give it as input is what is the slope, and it's actually the vector, because I care for the size of this vector, the length of this vector, but definitely the direction of the vector at A and the direction of the vector at B. That is that if I'll now start T start from 0 to 1, a fly cricket moves from 0 to 1, the cricket will start at A, will end at B, and the direction, your velocity at A, will direct according to your input, to what is V of A. Change the direction, you're changing the curve, of course at A itself, but the whole curve is changing according to it. And similarly, changing this vector at the endpoint, the whole curve is changing, but I guarantee that when the fly moves to B, that will be the final direction. Cubed puzzle, I'll let you meditate on it. I have 4 ants, slightly related to it, not really. I have 4 ants, they are forming a square of size 1 by 1 by 1 by 1. A tries to catch B, and how does it try to catch it? It always do dog walk, always walk in the direction of B, the ant B, which in turn tries to catch the ant at C, which in turn tries to catch the ant of D, and they're all moving in 1 mile per hour. And when they'll meet, they will create some strange curve, each one. And the question is, what's the length of this curve? Not exactly related, a bit related. That's a cute puzzle. What's the length of this curve? To express this curve, by the way, it's a cute differential equation, not in this course, but my only question is, what's the length of the curve? Okay, so back to Hermit. So I need the 4 parameters. Where is A, where is B, what is the direction of A, what is the direction of B. And how do I combine all of them is really cute to my taste. How do I create all of them? Well, I create a basis of 4 polynomials, each one of degree 3. I didn't mention degree 3 also important because we talked about finding the root. Let's assume that that's the part of a shape and I'm doing ray tracing. There is a vector coming away from your eye to the pixel, and I want to find where is this ray hit. This method that we just described of finding the root of polynomial of degree 3 will work just fine. You can find the exact point, and then you can find what is a normal at this point. You don't need it in hw5, but it's good to know. That's one of the reasons to play with only degree 3. If I have one shape and it moves, and I ask, does it hit another shape or not? Once again, degree 3. Everything works and very easy computational. Okay, how do I create the whole curve? I need to tell you for every time t, where is a point p of t. And it's really, really nice, and you'll find it in every textbook of graphics. Again, I'll give weights to each one of the 4 parameters, and the weight, understand it as A has x and y, V of A has x and y, and the weight is just multiply each one. H10 is H00, let's start from H00. If you care, that's a polynomial H00. Here it is formal. We don't need so much the formality of it. Let's look at the graph. What is H00? It starts at 1, and it's elegantly declined to 0. Okay, so H00 start at 1, declining when t equals 0, H00 is 1. When t equals 1, H00 is 0. What is H01? Just a mirror image. If you care, you have the formula, but it's just the mirror image. It's the same function, just replace instead of t, put 1 minus t. And already, if I have these 2 functions, and now I'm asking you, just let's think about these 2 functions, and let's now create H00 of t times A plus H01 of t times B. What is this, 2 guys? What happens at t equals 0? T equals 0, this is 1, this is 0, my fly is at A. What happens at t equals 1? This is 0, this is 1, just don't take my word, look at the graph. So I'm just at B. It's overkilling because I didn't need all of it, but it's, at least I know that I start at A and I start at B. What is H11 and H10? There is a formula, but we have ADHD, so we don't like all these notations. Let's just look at the graph. H01, take my word, its derivative at 0, its derivative, sorry, its value at 0 is 0, and its value at 1 is also 0. And the same goes with hw5. hw5 start at 0 and end at 0. It's not uniformly 0, but they both start at 0. So if I take this thing and plus hw11 of t v of a, hw11 it will be v of b. h11 of t, v of b. At t equals 0, it's 0. At equal 1, it's 0. So it doesn't have any impact about where the curve starts and stops. But why do I need it? And here is the whole Hermite curve. Hey, move. So here is the whole Hermite curve. It's A times A00, B H01. Notation is confusing, sorry about it. V of A times H10, V of B times H11. These two guys that start at 0 and end at 0 multiplying the direction, the orientation at A and B. Why do I care about it? Because to find the slope, the direction of the curve, I need to compute, to take the derivative of this whole expression, which is takes the derivative of each one of the individual guys. What you can prove, what Hermite proved, is that the derivative of this guy, both at A and B, is 0. So this guy has no effect on the derivative at 0 and 1. This guy, when you take the derivative, has no effect at 0 and 1. It will be 0 uniformly. What about this guy? What happened to it at 0? What is the slope? The slope is 45 degrees. It's 1, but it decays into a slope of 0. So what about H11? It starts at slope of 0 and go up to a slope of 1. Cool. So when I take the derivative and put 1, this dies, this dies, this dies, and this equal 1. And I put 0, then this equal 1, and all the rest dies. So what do I know about the summation? It started A, it started B, the orientation where it starts is V of A, the orientation when I end is V of B. Very elegant to just put them together. And now I can easily create a spline into it. How? I'll say my spline starts at A, ends at B, and ends of C, and I still have degrees of freedom. I can rotate the orientation of this vector V of B, which is also V of the next curve, any way I want. Don't have the GeoGebra, but fine. You can orient this guy anywhere you want. If you want this freedom, it's good. If you don't want this freedom, it's not a big deal. And the same goes to this orientation, this goes to this orientation. And what do I know about the whole curve, this whole spline? It started A, first segment started A and B, second segment started B and A. What about the orientation? If I make, since I decided just about one vector here, then the orientation by which I end at V, the orientation by which I end the first segment at B, is exactly the orientation by which I start the next segment. So it's smooth, not sharp, it's completely smooth, and it's even if you look at the second derivative, important for physics or dynamics, you do care about the second derivative, even computing nice texture mapping. The second derivative is also smooth. And you can go on and add more and more segments in this way. You just have this a bit headache of deciding what is this curve that you want to do. But the curve, the spline will be happy to cooperate with you, whichever parameters that you want to do. Catchmell-Rom splines tries to solve this issue and we'll get back to it. It will say, I only need the control point, and they play both the roles of point that I control as well as controlling the directions. It's a bit of a hack, but it's very, very useful hack. We'll get back to it. That might be the most popular out of all the curves that I'm presenting. Yeah, we already had these slides. Just to tell you together, I want to glue all the pieces one after the other. I want to get something smooth and so on. So we had the Hermite curve. Let's talk about a bit other parameters that I can care for. What is geometric smoothness? Sometimes it's relevant versus the geometric curve versus the algebraic curve. Let's look at the function cosine t and y equals sinus t, and cosine 2t and y equals sinus of 2t. The first one makes a circle, the second one makes two circles. If I make them connect at some points, is this good or bad? The orientation will be the same, but if you think about a fly that moves along it, oh, I completely forgot. That's a very good explanation. Why do I need this curve besides everything that I said? I forgot the very big application of all of it. Why do I want to generate these curves? And this time I do care about it. Because you're creating animation. You want characters to move according to these curves. And how are you doing the animation? You're not going to render each frame individually. You're taking frame 1, and a few seconds later rendering the next frame, a few seconds later rendering the next frame, and you want these curves to smoothly represent the motion between all these points. So what happened if I switch from sinus t to sinus 2t? The direction will stay the same, but what happened to my particle, a ball that moves along it, suddenly it starts moving twice the size, twice as fast. If you want it, it's fine, but be aware of it, that it's not smooth in terms of the velocity along it. All the curves that we described so far are smooth, and the second derivative is smooth as well. So we're getting it. Okay, Hermite curves discussed, just repeating the slide. Just repeating the slides, basically describe better what is a derivative, and it's nice that it's bases, if you like, the algebra around it, that are orthogonal bases in some sense, actually. And it's very easy to compute or to imagine from the input what the curve looks like. And all these parameters, notice that all these parameters are completely orthogonal. If I'm moving A, the curves will follow. Right? The curves will always start at A, the curve will always end at B, and it's completely independent of what I decide about the orientation from A and the orientation of B. Changing A will not affect the orientation, and changing the orientation will not affect where the curve starts. So it's orthogonal basis in the sense that it's 4 orthogonal parameters. Bezier. Presumably everybody heard about it. Everybody knows that it's Bezier, not Bezier. It's relative of Hermite. And we'll describe Bezier in a few ways. And again, you're losing me. It's very classical textbook. How do I get from Bezier to Hermite? So what is the input to Hermite? Hermite wants 2 points and 2 directions, start and end, and 2 orientation. Bezier, on the other hand, of degree 3, cubic Bezier want 4 points, but they are not equally privileged points. Bezier wants to have start point, end point, and 2 control points, A prime and B prime. And you'd like to think that A prime is just, that a vector from A to A prime is the input that we gave to the Hermite, which is almost correct. So the orientation at the beginning is toward A, and the orientation at the end of the Bezier is toward B. The magnitudes are a bit different. If you want to move from A to B, from Bezier to Hermite, you have to look at the length of the segment and split it by 3 when you're moving from one to the other. The same for this one. Not huge, but important. Nice property of Bezier. A prime, B prime. The curve is inside the convex hull of these 4 points. So again, if it's a spline, it follows all of them. Okay, always inside the convex hull of these 4 points, and Bezier and Hermite are quite related. You just need just use the vector from A to A prime. That's a vector that Hermite looks for, just with third the length, and similarly for the second vector. Okay, but and some people don't like this mixture that some points are privileged, that I have to go through the first point to the 4th point, and then from the 4th to the, not to the 6th, not to the 7th, to the 8th one, that's the point that I'm going to, and the other points are just of control points, so it's somehow asymmetric, and that's Quachel Rom tries to solve, as all points have the same privileged. You can go from one to the other by multiply by a very simple matrix, just change a bit the location. Not critical right now. Go from one to another, not critical right now. Everybody understand how to create the Bezier by using these polynomials, and everybody understands these polynomials. That's I want you to as a takeaway. Weights that changing within time, and take into combination all the 4 parameters, but at the very beginning and at the very end there is a special one. Bernstein polynomials, it's cool that it's suddenly combinatorics pops up. What is n times k? How many ways can you take k points out of n points where the order doesn't matter? A bit surprising that this polynomial suddenly pops up. Write it in this way, that Bezier curves, and it works also for higher degrees. Here are, once again, the polynomials by themselves. There is a 4 basis polynomial, just like we had in Hermite, slightly different for Bezier. What's very cool is, let's think about Bezier polynomial curves in yet another way. I have a point P0, and I want to create Bezier curve of dimension 0 is just this point. Let's have a line that goes from P0 to P1, and let's define a Bezier curve of degree 1. How? Let's call this parameter alpha, the ratio of this parameter. That's T, that's alpha. The total length is 1 minus alpha, or if it's combined. Or normalize it so the length of the segment is 1. And then every point in between will be alpha times P0 and beta times P1. Just a normal linear combination. Okay, I'm not surprising anybody. It's just a linear interpolation that we had so far. That's for creating Bezier curve of degree 1. It's not, giving different weights to each one of the endpoints, the first and the second. What I'm describing now is not a good algorithm to generate the Bezier. You can use the polynomials, you can use Bernstein polynomials if you need the Bezier, but it's cool. Here is a formula, a bit awkward, this alpha and beta. Let's understand what's going on with this alpha and beta. Remember, beta is 1 minus alpha. So now I want to create Bezier curve of degree 2. And to create a Bezier curve, I need to tell you at every moment t where is my fly is at time t. Assuming at t equals 0, I need to start at p equals 0. At t equals 1, I need to be at p2. And any time in between, I need to be on the curve somewhere in between. What's the idea about Bezier? Bezier of p1, p0, p1, p2. I'm creating a polynomial of degree 2. Degree 3 will be completely analogous. How? You gave me the time t, say t equal half. You want to ask what happened when t equal half, just at the middle of the time. What should I do? I'll look at the first segment, split it in ratio of t and 1 minus t, just half and half. That will be 1 point. I look at the second segment, split it in a ratio of half and 1 minus half. The alpha and 1 minus alpha, it's half and half. Put the middle of this point, of these two original segments. Now we created one new segment. Look at this new segment. Remember, I want to know where I'm at t equal half. Look at this new segment that you generated. Split this segment at ratio of t and 1 minus t, half and half once again. That's where the Bezier curve is t equal half. And the same goes when you're changing the time. So the animation out of it when you solved this beautiful polynomial, no it's not, is degree 3, again, 3 segment, sorry, degree 3, 3 segments, first one, second one, third one, at time t, takes the first one, split it in alpha, 1 minus alpha, give me this point. Second one, alpha, 1 minus alpha, second point. Third point, and now what do I do? Apply the same trick. I created one new polynomial, one more new polygonal path. Now, I started with a polygonal path of 3 segments. Next rule, at this fixed time, I have a polygonal path of only 2 segments, from which recursively you create a polygonal path of 1 segment. Recursively, you fix the point on this curve. And if you play with it a bit more, it's not hard to see where the Bernstein polynomial just appeared. Schwarzschild, finally, we are in something important. We ran out of time, so just one word. I want to tell you, here are all my control points, and I want to go through them, but I also want to have the weights depending on these control points, which means that for every point, if I want Bezier or line, I need to tell it a vector that should be reasonable. What should be this vector? Answer, takes the point before, takes the point after, takes the average. That will be the direction that pi corresponds to. Again, what is the slope of pi? It should be the average between the previous point and the next point. That should be the direction of this point. And that's how I both go through all these points, but also these points control the slope at each one of the points by controlling the next and the third. And that's like the most intuitive one. You'll draw a sequence of points, your curve goes through all these points, and will its slope behave reasonably well. And you don't need to overkill it by specifying other parameters. You still have the issue of what is the slope, what I didn't tell you. What do you still have to specify? What is the slope at the very beginning, at the very end that you do have parameters, because the last point doesn't have the next point to estimate its distance, so you either look at only the previous point or add one parameter that allows you to control it. Okay, thanks you. Next we'll start surfaces.